So we are looking at the shock tube problem, and we are looking at solving the left hand side of the shock tube problem, which initially you start off with a large pressure difference between the driver side and the driven side. On the right hand side, into the driven side, you have a shock wave, a moving shock wave, and behind it there is a motion of gas. On the left hand side, you have expansion waves. These are waves, isentropic waves, or they move without any change in entropy, and we are trying to address the left hand side of the shock tube problem, and they are waves. So we began with waves of very small changes or infinitesimal changes. Now we move on to waves of finite amplitude, or when the amplitudes of these waves are quite significant, what happens. So let us move ahead with the problem. So let us directly go to the equations of motion. This is for a fluid flow, so we go to fluid flow equations, and also is compressible in nature, so density is a variable. So take the continuity equation. You start with the continuity equation, d rho by dt, this material derivative, d rho by dt plus rho, this is divergence, this is the dilatation, del dot v is equal to 0. Okay, so we start with this equation, and we know that it's a nice isentropic flow. So density is a variable here, and it can be function of pressure and entropy. For an isentropic flow, change in density is 0, change in entropy is 0, so this is 0. And you get the term dou rho by dou p. Of course you should know dou p by dou rho at constant entropy is a square. So one can relate d rho by dt to dp by that is change in pressure. So they can be related to each other by using the acoustic equation, that is speed of sound 1 by a square dp by dt. Okay, so in the continuity equation, the change in density is or the material derivative of density is replaced by the material derivative of pressure. And why did this will soon become evident. So for a one dimensional flow, d by dt, the material derivative is dou by dou t plus u dou by dou x, where u is the velocity in x direction. Okay, so you can write the material derivative of pressure as so dou p by dou t plus u dou p by dou x, and plus rho dou u by dou x. So this form of the continuity equation, where we have used definition of speed of sound and brought in the pressure variable, and then it has been put here, and this is the converted continuity equation. Now we move to the momentum equation without any body forces or any viscous forces. It's an inviscid flow. So again, material derivative of velocity, and we are considering only one dimension, so this becomes dou u by dou t plus rho u dou u by dou x, and the gradient of pressure is dou p by dou x in one dimension. So this becomes the equation rho dou u by dou t plus rho u dou u by dou x plus dou p by dou x equal to 0. Now you have the two equations. The first equation was from the continuity equation, 1 by a square dou p by dou t plus u dou p by dou x plus rho dou u by dou x equal to 0, and the momentum equation is rho dou u by dou t, or it can be divided by rho also, so we can do that, u dou u by dou x 1 by rho dou p by dou x equal to 0. Now we do this operation, we multiply the continuity equation by a by rho, that is the speed of sound, by density, and add the momentum equation to it. So if you do that, you get 1 by rho a, this term, dou p by dou t plus u dou p by dou x plus a dou u by dou x, and the momentum equation is added to this, so plus dou u by dou t plus u dou u by dou x plus 1 by rho dou p by dou x equal to 0. So now if you collect terms or containing pressure and velocity separately, you get dou u by dou t plus, so there is a u here and a here, so it will be u plus a dou u by dou x plus, this is 1 by rho a here and dou p by dou t plus, there is a u here, and if a is taken out as common, you would have to multiply and divide this by a to take 1 by rho a as common, and then combine it with the other one, u plus a dou p by dou x. So that is a term that has been written over here, dou u by dou t plus u plus a dou u by dou x, that's 1 by rho a dou p by dou t plus u plus a dou p by dou x equal to 0. So this is what we get. Same operation, but now what you do is a by rho multiplied to continuity equation and subtract the momentum equation, and you can carry on the same steps now what has been described over here, and you can see that you end up with dou u by dou t plus u minus a dou u by dou x minus 1 by rho a dou p by dou t plus u minus a dou p by dou x equal to 0. Now what is the significance? You can see that there are two terms, u plus a and u minus a, they are quite significant, and this is where the application of method of characteristics comes into picture. So what we are looking for is some transformation. So these are partial differential equations, so is there some transformation that we can apply so as to convert them to more easily solvable differential equations, ordinary differential equations, and for hyperbolic equations, these are hyperbolic equations, then there is a method to do it, and that is the method of characteristics, and to understand this you can go back to our previous classes when we were looking at a general variable and looking at dou u by dou t plus c dou u by dou x equal to 0, where c is a constant of propagation, and we were looking how can we convert this to a ordinary differential equation, and u being a function of x and t, and it can be written, du can be written as dou u by dou t dt plus dou u by dou x dx, and comparing these two we sort of arrived at, if we consider dx by dt is c, then we can write this as du, or an ordinary differential equation, it can be taken to be du. So along lines dx by dt equal to c, okay, so along these lines which gives out the lines as x minus ct equal to some constant, x minus ct is a constant. So along these lines you can convert the partial first order partial differential equation into an ordinary differential equation. So this is the basic principle of method of characteristics, and you can always come back to this simple equation in order to understand what we are doing. So you can take the same principles here and come back to this problem that we have, which is more involved. You have both u and p, both are functions of space and time, x and t, and p is also a function of x and t. But you look at these equations, you have similar form, you have u plus a here. So along the lines dx by dt is equal to u plus a. So along these lines this particular form gets converted into dp, while this will convert to du, which is change in velocity. Okay. So now du is here, d represents total derivative. So here again there are another set of characteristics for this problem, which is u minus a. So there are two sets, one is u plus a, the other one is u minus a. So dx by dt is u minus a. So this set of characteristics is known as is generally called C plus, and this set is called C minus. That is the way it is represented. So if you do make those changes, then you get two equations. These equations are called as the compatibility equations, so they convert. So now by going along certain lines or certain curves in space which are related by dx by dt is equal to u plus a, this belongs to one set of characteristics which we call as C plus, and the other one is dx by dt is u minus a, another set of characteristics which we call as C minus. If you take separately in these two characteristics and go back and look at the equations, they transform into ODEs, du plus dp by rho a equal to 0 and du minus dp by rho a equal to 0. These are ordinary differential equations, they can be integrated. Okay. So now these so now you see in this discussion on finite amplitude waves, what we see here is that your speed of propagation of the waves is not a infinity anymore, it is u plus a and u minus a. These are the speeds with which the waves propagate, and a is not a constant. Speed with which it propagates in space and time can vary. So that is the important difference between infinitesimal waves, where you saw that the speed of propagation is the speed of sound, which is a infinity, but here it is not so. So now how would we proceed? We have to evaluate these integrals. So this is for C plus characteristic, the integral is j plus. These are called Reimann invariants because this has to be a constant if you integrate it. U plus integral dp by rho a is equal to a constant. So along a C plus characteristic. Secondly, if you integrate the second equation, that is this one, then you get u minus dp by rho a is constant along C minus characteristic. So this is along u minus a and this is along u plus a. This has to be borne in mind. Okay, it cannot be randomly done. So j plus corresponds to C plus, j minus corresponds to C minus. Now let's so this is quite general, this is dp by rho a, it is general. Now let us go into the specific case that we are discussing, that is to a calorically perfect gas. So if you take a calorically perfect gas, so you know a square is gamma p by rho, okay, this is known, and these processes that we are discussing here is isentropic. We are looking at the expansion waves that travel, so they are isentropic waves. So you know that isentropic waves or the isentropic process is related by p is proportional to t power gamma by gamma minus 1. So an arbitrary constant k1 is introduced, p is equal to k1 t power gamma by gamma minus 1, okay. And of course t is actually a square, okay. So a square is equal to gamma r t. So you can use this fact here. So t can be replaced by a square with of course other additional constants getting multiplied. So you get p goes as k2 t power or a power that is the speed of sound a power 2 gamma by gamma minus 1. This is how we get this, okay. Then once we have an expression for p, we can write dp, and dp is k2 2 gamma by gamma minus 1 a power 2 gamma by gamma minus 1 minus 1. This will turn out to be k2 dA 2 gamma by gamma minus 1. So you can do this gamma plus 1 by gamma minus 1, right. And we we have to do integral dp by rho a. Now we have expressed p in terms of a. Now can we express rho in terms of a? We can use this equation, a square is equal to gamma p by rho, or you can use rho is gamma p by a square. So you can use that equation, and you have the term rho a. So rho a is the term that needs to be evaluated. This is nothing but gamma p by a square multiplied by a. This is gamma p by a, and p is k2 a power 2 gamma by gamma minus 1. So rho a also turns out to be k2 gamma a power gamma plus 1 by gamma minus 1. Now dp by rho a, now this term dp by rho a will now turn out to be if you put things together, there is a 2 here, this gamma gets cancelled with this gamma, k2 goes off with this k2. So you have 2 by gamma minus 1, this a power gamma plus 1 goes by this a power gamma plus 1. So you are left with dA, integral dA. So what you get is integral dA is a. So u plus 2a by gamma minus 1. So the Reimann invariant can be solved analytically. You can get closed form solution u plus 2a by gamma minus 1 is equal to constant along a C plus characteristic. Similarly for a C minus characteristic is the same integration, but you have this negative sign here. So u minus 2a by gamma minus 1 is constant. So if you take any so the way to solve these is starting from an initial problem or initial value, you draw the C plus and C minus characteristics. So they do go like this, and you know the u of, you know the solution x, the initial solution a at x comma 0, this is known. So at intersections of the C plus and C minus characteristics, you evaluate u and a, because along a particular characteristic, whether you take, so if you take this is C minus characteristics, this is C plus characteristic. So along the C minus characteristic J minus is constant, along C plus characteristic J plus is constant. So it can be evaluated starting from the initial value. So this is initial line, and at any point you can solve them by just an algebraic manipulation, a solution of simultaneous equations. A is gamma minus 1 by 4 j plus minus j minus, and u is half of j plus minus. So you have to look at, so it is j plus plus j minus. Okay, so this is the equations. So for solving a and u separately. So the way the solutions of this kind are done is you have an initial line, and then you can solve the field at any space and time. Okay. So now let us go and just compare whatever we had done in the previous class to this class. Previous class we had very small waves, infinitesimal waves, and this class we had finite waves. Now infinitesimal waves are very small, and they propagate at constant velocity, which is a infinity. So when they propagate, an initial disturbance propagates with the same form, it does not change form, because it is just propagating, all parts of the wave are propagating with the same speed, a infinity, it does not change form. So the shape stays the same, and the equations are linear hyperbolic equations. Typically these are sound waves, representative of sound waves. But if you come to finite disturbances, then the change is quite significant, and so these waves, they do not travel all the time with the velocity a infinity. They travel with propagation speeds u plus a or u minus a, and it can vary from space and in space as well as at different times, instant of times. So because of this variation, the initial shape of the wave, it changes with time, so it gets deformed, and these equations are fully non-linear. So how can we apply this to shock waves, shock tube problem? To get the connection, we need to understand a little bit about how these characteristics behave. So if you have a region of uniform flow, that is the velocity, pressure or temperature do not depend on space and time, and there you draw the characteristics C plus and C minus. The C plus and C minus are nothing but dx by dt is u plus a, and this is C plus, and dx by dt is u minus a, this is C minus. So if you draw them at all points, u and a are the same. So you can take them as u infinity, a infinity, so they will same everywhere in a uniform flow field. Therefore dx by dt is the same along u plus a and u minus a. So you have two sets of straight parallel lines, so they are always parallel, they are straight in a uniform flow. While if you take a completely non-uniform flow, that is represented here represented here, u and a are not constant anywhere, so in general they are changing everywhere. So they at every point, of course you will have dx by dt is u plus a, but as you move away from the point you have another u plus a or u minus a. As a consequence, these are curves, they are not straight lines, and so you have two sets of curves. Okay, so this is completely non-uniform flow. Both is, so an intermediate between these two is a simple non-uniform flow. It occurs when you have a region of non-uniform flow bounded by two uniform flows, and if you think of it, this is typical in a in the expansion side of the shock tube, where you have region 4 here and region 3 here. Region 3 is uniform, you have pressure is P3, speed is U3, and region 4 is having no velocity, it has pressure P4, T4, U4 is 0. Okay. And the expansion waves move between them. Okay. So you have a non-uniform flow, which is the motion of the expansion waves between two regions of uniform flow. So that follows the simple non-uniform flow problems. Okay, so that is how it comes into picture, and what is important there is an understanding that when you have such a flow, so we already talked about uniform flows. Here it is always straight, that is rather straightforward. But if you have a simple wave region, a region where it is a simple non-uniformity, not completely non-uniform, then you have a property that one set of waves, either one set, either C plus or C minus, it depends on the problem. One set of the waves will be straight lines, the other one will be curved, and you can show that simply by considering the case that you have a non-uniform region here and you have a uniform region here, and this forms the boundary of non-uniform region and a uniform region. So consider, so these are C plus characteristics here and C minus characteristics are coming in, they are coming in here from the non-uniform region. So so you can consider these 2 points. This is a uniform flow, while P Q lie in the non-uniform flow along the C plus characteristics. Okay. So if you do look at that problem, then what you can show is, so along C plus dx by dt is u plus a. Okay. But C minus characteristics are the ones which are moving from the uniform region to the non-uniform region. So along C minus characteristics, the J minus, that is Reimann constants, are invariant. So you can write up minus 2ap by gamma minus 1 equal to ua minus 2a by gamma minus 1. Similarly you can write it for points q and b. So these 2 equations you can write, but since it is coming in from uniform region, a and b, ua and ub, they are the same. So as a consequence you can get that up equal to uq and ap equal to aq. So along the C plus characteristic, essentially up and uq, they are here along the C plus characteristic in the non-uniform region, but they have the same value. That means the C plus characteristics have the same dx by dt at p is equal to dx by dt at q, and their values are also the same, they are straight lines. So this is the picture that comes out, that you have a region of uniform flow, another region of uniform flow, in between if you have a non-uniform flow, then one set of characteristics are straight lines, the others are curved. So keep this idea in mind, because this is important when we now look at the shock tube in whole, and region 3 and region 4 are uniform regions which bound. So this is region 4, this is region 3, and in between you have the expansion waves. So the expansion fan lies in between those 2, and this information is useful when we look at the solution of the shock tube problem.